Nuclear quantum computing. It is coming. A trio of separate research teams from 3 different continents published individual papers indicating similar quantum computing breakthroughs yesterday. All 3 were funded in part by this army, and each paper appears to be a slam dunk for the future of quantum computing. But only one of them heralds the onset of the age of nuclear quantum computers. Maybe it's the whole concept of entanglement. But for a long time it's felt like we were suspended in a state where functional quantum machines were both right around the corner and decades or more away. But the past few years have seen a more rapid advancement toward functional quantum systems than most technologists could have imagined in their wildest dreams. The likes of IBM, Microsoft, D-Wave, and Google putting hybrid quantum systems on the cloud coupled with the latter's amazing time crystal breakthrough have made 2018 to 2021 the opening years of what promises to be a golden age for quantum computing. Despite this amazing progress, there are still holdouts who believe we'll never have a truly useful, fully functional, qubit-based quantum computing system. The main reason given by these cynics is usually because quantum systems are incredibly error-prone. The 3 new papers published yesterday should go a long way towards shutting those critics up because each of them manages to address the error correction problem in quantum computing by essentially going back to the drawing board. The first 2 teams, one from Tokyo and one from Los Angeles, went about the issue in a similar way, while the Australian team decided to take a different approach. In fact, it's worth noting that all 3 teams shared various resources in order to help facilitate each other's research. The result is that each team was able to build a distinct, silicon-based, 2-qubit quantum computing system capable of operating with greater than 99% accuracy. That's pretty cool. But dozens of quantum research centers including IBM's, Google's, and Microsoft's have all developed functional quantum gate systems with dozens or even hundreds of qubits. IBM and Google, for example, both claim they've reached quantum advantage, or the point where their quantum computing systems can do things that no regular classical computing system could. But here in 2022 we're not talking about being able to flip a switch and do quantum calculations. We're talking about cutting-edge computation systems that require enormous resources to pull off incredibly specific feats. You can't just upload a neural network to a quantum computer and expect to act like it's been supercharged. The algorithms we're currently able to run on cutting-edge quantum systems are more like super challenging math problems that can still be verified using classical means. Unfortunately, the long and short of it is usually, the more qubits you have, the more errors you get. The new research hopes to alleviate that by creating a new way to handle qubit operations, thus allowing gate-based quantum computer systems to scale. And, right now, scalability is the single largest hurdle standing in the technology's way. It's actually fairly simple. All 3 teams are trying to put qubits on a silicon chip. As Ars Technica's John Timmer pointed out yesterday, this plays to our current engineering strengths. What we found most interesting, however, is the mind-boggling way in which the Australian team managed to create a pair of nearly errorless qubits. They went nuclear. In a press release from the University of New South Wales, Meta C. Modzik, a lead author on the Australian team's research paper, described how entangling an electron with the nuclei of 2 phosphorus atoms allowed them to control them as qubits without losing information. Per Modzik, sure it is. They're not splitting atoms or fusing them, so there's probably a pretty close to 0 chance that nothing bad will happen. We exploit atoms to do all kinds of things that don't involve blowing up entire cities. In this case, the Australian team is exploiting a feature of entanglement that allows them to force communication between qubits that normally would either hoard their information or lose it too quickly for use. It's likely just as safe as using lasers to create qubits out of light, maybe even safer. But the researchers are hoping it's the foundation for a paradigm that will be much easier to scale than other systems. At the end of the day, this is all exciting news. It's rare to see a peer-reviewed quantum computing breakthrough because the field is incredibly challenging. Getting 3 in the same day is a eureka moment in its own right. Of course, it could take a while for these early experiments to pan out and turn into full-fledged quantum computers. But if we take these papers as a proof of concept for the future, things look incredibly bright. You can read more about quantum computing artificial intelligence, and the wacky world of physics and other mind-blowing future tech right here on Neural.